Welcome back to the Deep Dive. We sift through the noise to bring you, well, hopefully, the clearest insights on tech history and its impact. Today, we've got a story that, honestly, it sort of flips the script on how we usually think about where modern computing came from. The typical image is maybe the garage startup, right? Silicon Valley pioneers. But the sources we're diving into today point somewhere else entirely. Somewhere older, maybe more surprising. Military necessity. Specifically, naval warfare in the early 20th century. That's where the spark, the real ignition for the digital revolution seems to have happened.
It's a fascinating thread to pull on, isn't it? What we're going to do is trace that lineage. We'll look at the foundational technical solutions step by step that emerged from these really practical, often incredibly urgent challenges in naval defense. And we'll follow that thread right through to the complex network systems you interact with every single day. This isn't just a history lesson for the sake of it. It's really a crucial look at how these deep roots shaped, well, pretty much every layer of our digital world. We want to uncover those often unseen catalysts, those technical breakthroughs that really made it all possible.
And it's quite a story. I think understanding this history gives such vital context for, the tech advancements happening right now. It really shines a light on that critical interplay, the push and pull between government, academia, and industry. That dynamic is still driving innovation today. It also maybe challenges some common ideas about where truly groundbreaking tech originates. So, okay, let's unpack this journey. Where do we start? You mentioned naval warfare sparking the digital fire way back when.
Right. To really get it, we need to set the stage. We're talking early 20th century, think 1900 to maybe 1925. The term digital computer didn't even exist yet, not in any practical sense. But naval warfare, that was already incredibly complex, and the fire control systems needed to manage it. They were pushing the limits of existing technology. Think about it. Directing huge guns on moving ships, trying to hit other moving ships, coordinating a whole fleet, processing this constant flood of battlefield information in real time.
Okay, yeah, that sounds incredibly demanding. So what kind of problems were they actually trying to solve on a technical level? What were the big hurdles?
The hurdles were immense. These weren't just abstract math problems. They were dynamic, real-time challenges demanding rapid, precise calculations. And the tech they had simply couldn't deliver reliably. You had mechanical calculators, analog electrical systems, but the speed, the accuracy, the sheer volume of data, it created this huge technical bottleneck. A bottleneck with, frankly, life or death strategic implications.
And the tools they were using must have been pretty rudimentary by today's standards. You said analog.
Absolutely. Heavily reliant on mechanical gears, cams, analog electrical circuits, and combined with just immense manual human effort. Picture a ship's Combat Information Center, the CIC. It was basically a dedicated room where all the incoming intelligence, radar, sonar, visual sightings was supposed to come together. Operators would feed this raw data in, and then teams of sailors would literally plot positions and movements by hand on shared maps or plotting boards.
Wow. So like those scenes in old war movies with people pushing little chip models around a map table.
Conceptually, yes, very similar to the Battle of Britain bunker idea, but crammed onto a warship in the heat of battle. Crewmen painstakingly updated this shared map display, and commanders had to make critical decisions based on this picture, which was always slightly out of date, always manually compiled.
That sounds incredibly labor-intensive, obviously, but also just ripe for error, especially under pressure. What were the specific technical weak points of that analog approach? Where did it really fail them?
Well, there were several core problems. First, the unreliability. Analog circuits, especially those with mechanical parts, they just wear out, they break down, they needed constant calibration. Plus, their signals were incredibly sensitive to noise, electrical drift, even temperature changes. That meant imprecision at every step. Converting a radar blip to a plotted point, calculating a firing solution, each step introduced potential errors. Maintaining consistent voltage across hundreds of components, really, really difficult. And second, the human factor. The manual plotting, the constant updates introduced delays. Unacceptable delays in fast-moving combat. And under the stress of battle, human error was inevitable. A tiny miscalculation, a wrongly plotted point, could mean missing a target completely. Catastrophic consequences. So you had this clear, urgent technical need, these incredibly complex real-time challenges met with tools that were fundamentally limited in speed, accuracy, and reliability. That constraint, that desperate need for faster, more accurate calculation, that's really where the whole idea of a digital approach started to gain traction.
Okay, so they're hitting a major wall with analog, a huge bottleneck in getting reliable information fast enough. What was the breakthrough? The project that started to change the game?
Right. That brings us squarely to Project Whirlwind. And its origin story is, well, it's not what you might expect. It didn't start as some grand plan to build a general-purpose computer. Nope. It came from a very specific, very practical, and very urgent request during World War II. In 1944, the U.S. Navy went to MIT's Servomechanisms Lab. Their request, build us a flight simulator.
A flight simulator? Seriously, that's the seed for the digital revolution. That feels almost mundane compared to the outcome.
It does, doesn't it? But this wasn't just any simulator. The Navy's vision was incredibly ambitious for the time. They wanted a system that could continually update a simulated instrument panel based on what the pilot was doing with the controls. And crucially, they wanted a considerably more realistic aerodynamics model than anything that existed, something that truly felt like flying a real plane. Its original name was pretty descriptive, the Airplane Stability and Control Analyzer, or ASCAE.
Okay, that sounds complex. How did trying to build a super realistic flight simulator lead to these fundamental computer breakthroughs? What technical walls did they hit?
This is where Whirlwind starts to pivot from just a simulator project into a true digital computing pioneer. By the time it was operational, around 1951, Whirlwind was, and this is key, among the first digital electronic computers that operated in real time for output. And it was the first that was not simply an electronic replacement of older mechanical systems. It was fundamentally different.
Real time. What does that mean in this context, and why was it so different from, say, ENIAC?
Great question. Real-time operation was the absolute game changer here. Earlier computers like ENIACs mostly worked in batch mode. You'd feed them a stack of punch cards, wait sometimes hours, sometimes days, and eventually get a printout with the results. But a flight simulator, it has to react instantly. When the pilot moves the joystick, the simulated plane has to respond now. It needed constant input, constant calculation, constant output, feeding back to the instruments. That demanded speed, continuous operation, and unwavering reliability in a way batch computers just didn't. This relentless demand for real-time interaction fundamentally reshaped how they had to think about computer architecture.
Right, it's interacting with the world, or a simulation of it, moment by moment. That's a totally different design philosophy. What other technical firsts came out of Whirlwind?
Another big one was bit parallel calculation. Instead of processing the bits, the zeros and ones, one by one in sequence, Whirlwind could handle multiple bits at the same time, in parallel. Think of it like having multiple lanes on a highway instead of just one. It massively boosted calculation speed, especially for the kind of complex math needed for aerodynamics. But probably the single most critical breakthrough, the thing Whirlwind is most famous for, technically speaking, was magnetic core memory.
Magnetic core memory. Okay, that sounds important. What was it replacing, and why was it such a big deal?
It replaced technology that was, frankly, holding everything back. Earlier computers used things like electrostatic storage tubes, basically modified cathode ray tubes or mercury delay lines. Mercury delay lines stored data as sound waves traveling through a tube of mercury, slow, bulky, temperature sensitive, and the data vanished if the power flickered. You had to constantly refresh it. Williams tubes, using CRT screens, were a bit better, but still notoriously unreliable and needed constant refreshing too. Imagine trying to run a complex simulation if your computer's memory kept forgetting things.
Yeah, that sounds like a nightmare for reliability, especially for a real-time system.
Yeah.
So magnetic core solved this. How'd it work?
It was a revolutionary step. Led by J.W. Forrester and Bill Papian at MIT, they started developing it around 1949. They used these tiny donut-shaped rings made of ferromagnetic material, ceramics, mixed with metals maybe the size of a pencil eraser. Wires were threaded through these cores. By sending electrical pulses through the wires, you could magnetize a core in one direction, representing a 1, or the other, representing a 0. The key was, once magnetized, the core stayed magnetized. It held the data without constant refreshing. It was non-volatile, at least compared to the earlier tech, and it was fast. They achieved switching speeds about 300 times faster than the alternatives. Reliable, stable, fast memory. It was the missing piece.
Wow, 300 times faster and stable. That's not just an improvement, that's transformative. It basically enabled reliable digital computing, didn't it?
It really did. It provided the stable, high-speed internal memory that these complex, real-time systems desperately needed. Suddenly, the computer could reliably hold and instantly access large amounts of data and instructions, which is fundamental for anything beyond simple calculations. Before core memory became viable around 1953, Whirlwind was reportedly down for maintenance about half the time because of memory failures using those older electrostatic tubes. Core memory changed everything.
Incredible. Were there other innovations happening at the circuit level, or maybe even how they kept the machine running?
Oh, yes. On the circuit side, they were using things like the Eccles-Jordan flip-flop circuit, a fundamental building block for digital logic, basically an electronic switch that holds a single bit. They were constantly iterating, trying new vacuum tubes like the 7AD7, even redesigning sockets as better components became available. It was a continuous refinement process. But what was also really advanced for the time was Whirlwind's built-in self-diagnosis capability.
The computer could check itself for errors.
Exactly. They designed specific programs, check problems, and trouble location problems that the machine would run on itself to pinpoint faults. And it wasn't just finding parts that had already failed completely. It could actually detect marginal components, tubes, or other parts that were starting to degrade but hadn't failed yet. They could, for example, slightly lower the voltage to a specific tube section. If the tube was weak, this would push it over the edge and cause an error that the diagnostic program could then trace back to that specific component. It was an incredibly early, sophisticated form of predictive maintenance. Really quite brilliant.
That is brilliant, finding problems before they crash the whole system. But all this cutting-edge research, custom components, constant redesign, it sounds incredibly expensive. Was the budget an issue?
Ugh, a massive issue. The costs just spiraled. Remember that initial estimate? $75,000 for the study phase back in '44. By 1945, the estimate for completion was $875,000. Later that year, it was burning through $30,000 per month. By 1947, the total projected cost hit nearly $3 million. And get this, by 1949, Project Whirlwind was consuming almost 65% of the entire mathematics research budget for the Office of Naval Research, ONR.
65% on one project. That must have caused some serious friction. How on earth did Forrester justify that kind of spending, especially as the Navy was maybe losing interest in the original flight simulator idea?
There was definitely friction. Forrester had this strong first-class philosophy. He truly believed that cutting corners early on would cost more in the long run through delays, failures, and redesigns. He insisted on quality, on pushing the state-of-the-art, arguing that computers offered immense military potential, maybe even greater than radar. But that didn't stop the criticism. There was a major blow-up in the fall of 1948. Dr. Mina Rees, head of ONR's math branch, was deeply skeptical. She reportedly complained about too much talk and not enough machine, questioned the project's mathematical competence, and compared it unfavorably to von Neumann's IAS computer project at Princeton, which seemed more focused on pure computation.
So serious doubts internally and from the primary funder, the Navy, whose original need was fading. How did Whirlwind survive this? What saved it?
Geopolitics, essentially. The huge turning point was the Soviet Union detonating its first atomic bomb in August 1949. Suddenly, the continental United States felt vulnerable to air attack in a way it never had before. The focus shifted dramatically towards air defense. A high-level committee was formed, the Air Defense System Engineering Committee, or ADSC, often called the Valley Committee. They advocated for a comprehensive, integrated, systems-oriented approach to air defense, not just better planes or radars in isolation. And crucially, they looked at Whirlwind with its real-time processing, its developing reliability thanks to core memory, its potential for handling vast amounts of data, and saw it as the perfect nucleus for this continental air defense system. It offered a new, incredibly urgent mission just as the Navy's interest was drying up. The Air Force stepped in, under something called Project Claude, and effectively took over funding, redirecting Whirlwind towards this massive air defense goal.
Wow. Talk about a pivot. So this project, born for flight simulation, facing technical nightmares and budget battles, finds a completely new life because of the Cold War. What does that tell us about how innovation actually happens, especially when driven by military or strategic needs?
It tells us innovation is rarely a straight line. The urgent military need first for the simulator, then for air defense, provided the impetus and, critically, the sustained long-term funding for incredibly high-risk research. This was research that private industry at the time likely wouldn't have touched. The commercial payoff was just too uncertain, too far off. Forrester's expensive first-class approach, while controversial, forced fundamental breakthroughs like core memory and real-time processing. These had applications far beyond just defense. The technical challenge of simulating flight realistically pushed the boundaries of computation in ways that indirectly benefited almost all computing that followed. It shows how tackling really hard, practical problems can spin off fundamental advances with completely unforeseen, widespread benefits. Urgency can be a powerful, if sometimes costly, driver of deep innovation.
Okay, so Whirlwind gets this new mission, this new lease on life, focused on air defense. What was its most direct, large-scale legacy? Where did all that innovation get deployed?
Its most direct and arguably most monumental legacy was becoming the heart of the U.S. Air Force's SAGE system. That stands for Semi-Automatic Ground Environment. The core design of Whirlwind MI was refined and adapted into what was called the Whirlwind 2 design, and that became the central computer for the SAGE network.
Right, SAGE. Here's where it gets really interesting, I think. How do you go from one groundbreaking but still single computer whirlwind to building the computing backbone for an entire nation's air defense? And what were the ripple effects, maybe unintended consequences, of building something on that unprecedented scale?
SAGE was an absolutely colossal undertaking. Its goal was to provide real-time, unified air situation awareness covering all of North America. Imagine a network connecting dozens of radar stations, ground observer posts, patrol aircraft, naval ships, all feeding data into regional command centers. Each center housed massive computers based on that Whirlwind secondary, designed processing this torrent of information, displaying it on interactive consoles, and helping operators direct interceptor aircraft and missiles. It was conceived as a real-time control system, a real-time communication system, and a real-time management system, all integrated together.
That sounds astronomically expensive. Given the earlier fights over Whirlwind's budget, how did they manage to fund SAGE?
It was astronomically expensive. Estimates range from $8 billion to $12 billion in 1950s and 60s dollars. That's just a staggering figure. It was one of the largest defense contracts ever at that point. But the perceived threat after the Soviet bomb was immense, so the funding materialized. The first SAGE Direction Center went live in 1958, and by 1963, there were 23 of these hardened, complex centers deployed across the U.S. and Canada. But here's a key point about its impact, beyond just its military function. SAGE became an incredibly important, though perhaps unintentional, training ground.
Training ground, in what sense?
Think about it. Building and operating SAGE required thousands of engineers, programmers, technicians, and operators skilled in areas that barely existed before. Real-time systems, large-scale networking, interactive computer graphics, massive software development projects, human-computer interaction under pressure. Many, many pioneers of the modern computing industry got their start, learned their craft, working on SAGE in the late 50s and early 60s. Even though the system became somewhat strategically outdated relatively quickly, the primary threat shifted from bombers to ICBMs after Sputnik in '57. The human capital it created was invaluable. This massive government project essentially seeded the entire nascent computing industry with a generation of highly trained, experienced people. That legacy, the people, might have been even more important than the hardware itself in the long run.
That's a really crucial point. So the investment wasn't just in machines, but in people and skills that then flowed out into the wider world.
Precisely. And this marks a really important transition point in our story. We're moving from these very specific military-driven projects like Whirlwind and SAGE towards the formalization of computing as its own scientific field and the diversification of its applications beyond defense.
Right. So it wasn't just about building bigger, faster machines anymore. It was also about creating the theoretical foundations, the tools, the languages, and training the people who would shape the future of computing. How did computer science actually emerge as an academic field from these roots?
The 1960s were really the key decade for that formalization. You started seeing dedicated computer science departments being established at major universities. Stanford, Carnegie Mellon in '65, MIT in '68. These became hubs of research and education. And often the faculty were people who had direct experience with those big, complex, early projects like Whirlwind or SAGE. They brought that practical knowledge into academia. They started developing the curriculum, the theories, the mathematical underpinnings needed to establish computer science as a rigorous discipline in its own right, separate from just electrical engineering or mathematics. This was vital for creating a pipeline of future innovators.
And a huge part of making computing more accessible must have been developing better ways to actually program these machines, right?
Yeah.
Moving beyond toggling switches or writing raw machine code. Grace Hopper's name always comes up here.
Yeah, absolutely. And the Navy continued to play a really pivotal role here, sponsoring Grace Hopper and other pioneers throughout the 1950s. Their focus was on developing what they called automatic programming techniques, what we would now call the first compilers. A compiler is essentially a translator program. It takes code written in a high-level language, something closer to human language, and translates it into the low-level machine code, the zeros and ones, that the computer's processor can actually execute.
And why was that such a leap?
It was monumental because it abstracted away the incredibly tedious, error-prone, machine-specific details. Before compilers, programmers often had to write in assembly language, which is just one step above raw binary, or sometimes directly in binary. It required intimate knowledge of the specific hardware. Compilers meant you could write programs that were more readable, easier to debug, and potentially portable across different types of computers. It opened up programming to a much wider group of people, not just hardware specialists.
And Hopper was famous for making these complex ideas understandable, wasn't she? I remember hearing about her nanoseconds wire.
Yes, she was brilliant at communication. She famously carried around pieces of wire about a foot long, 11.8 inches, to be precise. She'd hand them out and say, "This is a nanosecond." It represented the distance electricity or light travels in 1/1000th of a second. It was a tangible way to make people, especially skeptical admirals or executives, understand the physical limits of speed and why minimizing wire lengths inside a computer was so important. A concrete way to grasp an incredibly abstract concept.
That's fantastic. And her work led directly to specific languages.
Yes, she was instrumental in defining common business languages. Her work heavily influenced the development of COBOL, Common Business-Oriented Language. The Pentagon actually pushed for this, convening a meeting in 1959 to define a standard language for business data processing. The first COBOL compilers emerged around 1960. The goal was readability and portability for applications like payroll, inventory, the bread and butter of business computing. And it wasn't just COBOL. Other key early languages also received significant government support, like John McCarthy's LISP. LISP was designed for symbolic computation, not just numbers, making it crucial for early artificial intelligence programming. These high-level languages fundamentally changed software development. They allowed for larger, more complex programs and broadened participation enormously.
Okay, so we have hardware breakthroughs driven by military needs, the emergence of computer science as a field, and now the development of software tools like compilers and languages, often with government backing. What was the next big catalyst? I know DARPA plays a huge role.
Exactly. DARPA, the Defense Advanced Research Projects Agency, is absolutely central to the next phase. It was established in 1958, remember, as a direct response to the Soviet Union launching Sputnik. The U.S. realized it needed a dedicated agency focused on high-risk, high-payoff research to prevent future technological surprises. DARPA wasn't focused on immediate military applications, but on long-term, potentially revolutionary science and technology. And within DARPA, one office became particularly influential for computing. IPTO, the Information Processing Techniques Office.
Right, and IPTO was led for a crucial period by JCR Licklider, who had this really forward-thinking vision of human-computer interaction, not just calculation, but something more symbiotic.
That's the perfect word. Man-computer symbiosis. Licklider, who headed IPTO starting in 1962, had this radical vision. He didn't see computers just as giant calculators or tools for automation. He envisioned them as partners, as tools for augmenting human thought and creativity. He wanted computers to help humans think better, solve problems more effectively, be more creative. He used this wonderful analogy of the fig tree and a specific species of wasp. They're completely interdependent. Neither can survive without the other. Together, they thrive. He saw the future of humans and computers like that, a tight cooperative coupling where each enhances the other's strengths. This is a profound shift away from just number crunching.
That's a fascinating analogy. A partnership, not just a tool. How did IPTO, under Licklider, translate that vision into actual funded research? What came out of it, technically?
Licklider's vision directly fueled IPTO's funding for one particularly seminal project. Project M at MIT, starting in 1963. MMA was an acronym with multiple meanings layered in: man and computer, machine-aided cognition, and multi-access computer. Licklider explicitly aimed for a profound advance in the way of thinking about computing. The emphasis was squarely on interactive computing and time sharing. He believed computers should be as much for communication as they are for calculation, really for seeing our networked world.
Interactive computing and time sharing. These sound like foundational steps toward the personal computing we know today. What were the tangible outcomes of Project MA?
Hugely foundational. Project MC was instrumental in developing and popularizing time-sharing technology. This allowed many users, often dozens, to connect to and interact with a single powerful mainframe computer simultaneously, typically through terminals. This made computing resources vastly more accessible and affordable on a per-user basis. Instead of waiting hours for batch results, users could type commands and get immediate responses. It fostered a whole new way of working interactively. By the mid-1970s, time-sharing was widespread on mainframes and mini-computers, thanks in large part to the work pioneered at Macs.
Okay, so making computers interactive and shareable. What else came out of NAFTA? I think you mentioned connections to things like word processing.
Yes, the concepts explored at MSc laid the groundwork for so much we take for granted. Early ideas for text editing and formatting, which evolved into word processors. Interactive programming environments where you could write and debug code on the fly. Even the core idea for the electronic spreadsheet organizing data in rows and columns that automatically recalculate has roots in this era, eventually leading to VisiCalc, Lotus 123, and then Microsoft Excel. And significantly, the successors to Project MC at MIT's Lab for Computer Science also developed the first versions of key internet protocols for personal computers, like the basis for FTP software.
So we're seeing a direct line from this defense-funded research into interactive computing, time sharing, and even the precursors to everyday office software and internet tools. This wasn't just about military advantage anymore.
Not at all. It raises that really interesting question. How does a defense agency like DARPA, focused ultimately on national security, end up catalyzing things as fundamentally civilian as spreadsheets and word processors? The answer seems to lie in their willingness to fund fundamental, long-term, high-risk research. They provided stable, multi-year funding to centers of excellence like MIT. This created the environment, the talent, the resources, the intellectual freedom for foundational breakthroughs. While the initial justification might have been defense-related, for example, better command and control systems through interaction, the underlying technologies developed, like time-sharing or graphical interfaces, turned out to have incredibly broad, unpredictable civilian applications. It shows the often unexpected dividends of investing in fundamental science.
And speaking of unpredictable dividends in DARPA, perhaps the most significant legacy of all is the ARPANET, the direct precursor to the internet. How did that come about? What was the core technical idea?
The core idea, the absolute bedrock of the ARPANET and the modern internet, is packet switching. Pioneering research by people like Larry Roberts at MIT Lincoln Lab, Paul Barron at RAND, and Donald Davies in the UK led to this concept. Instead of creating a dedicated, continuous connection between 2 points for a whole communication session, like the old telephone network did, circuit switching, packet switching breaks the data, email, files, web pages into small, discrete chunks called packets. Each packet gets an address for its destination. These packets are then sent out into the network independently and find their own way to the destination, potentially taking different routes. The network routers figure out the best path. This makes the network incredibly efficient. Links are only used when packets are actually flowing and remarkably resilient. If one path gets congested or fails, packets can just be rerouted.
Right. That resilience sounds like something the military would be very interested in, building a network that could survive damage. So ARPANET was built using this packet switching idea.
Exactly. DARPA's ARPANET program, which really got going in the late 1960s and became operational in the 70s, was designed with several goals in mind. Yes, resilience was one, but also linking researchers at different universities and institutions across the country to allow them to share expensive, scarce computing resources more efficiently. It started small, just 4 nodes in 1969 connecting UCLA, Stanford Research Institute, SRI, UC Santa Barbara, and the University of Utah. But it grew quickly. By 1971, it had 23 nodes. A public demonstration in 1972 really showed the world the potential of this new kind of network.
And what about the actual language of the internet? The protocols that allow all these different computers to talk to each other?
That was the other absolutely crucial piece. The development of TCP/IP, the Transmission Control Protocol and Internet Protocol. This work was done collaboratively by researchers at Stanford, BBN, the company that built the ARPANET's routers, and University College London, among others, primarily in the mid-1970s. TCP/IP provided the standardized set of rules, the common language, for how packets should be formatted, addressed, sent, and reassembled. It allowed different networks running on different technologies to interconnect seamlessly. That's the internet part, connecting networks together. It's still the fundamental protocol suite underlying the global internet today.
And once the network and the protocols were in place, what were people actually using it for in those early days?
Well, besides just accessing remote computers, 2 early applications, or apps, became incredibly popular, almost unexpectedly so. First was email. Ray Tomlinson at BBN is credited with developing the first network email system in 1971, famously choosing the @ symbol to separate the username from the host machine name. Email quickly became the killer app of the ARPANET, revolutionizing how researchers collaborated. The second was FTP, the File Transfer Protocol, which allowed users to easily move files between computers across the network. These tools dramatically accelerated scientific collaboration, allowing researchers to share data, drafts, and results almost instantly across vast distances.
So it started connecting people, not just machines.
Yeah.
How did it grow beyond the initial ARPANET community into something bigger? Was it always intended to become the global internet?
Not explicitly at first. ARPANET management was transferred from DARPA to the Defense Communications Agency in 1975. Around the same time, other federally funded specialized networks started popping up for different scientific communities. MFENet for fusion energy, HEMET for high-energy physics, NASA's Space Physics Analysis Network. This showed a growing demand. But many universities still weren't connected. That's where the National Science Foundation, the NSF, stepped in during the early 1980s. They created CSNet to connect university computer science departments that weren't on ARPANET. CSNet was a huge success, demonstrating the value for the broader academic community. That led NSF to fund the much more ambitious NSFNet in 1986. NSFNet created a high-speed backbone network connecting NSF's supercomputing centers and regional academic networks across the country. It essentially became the main non-military backbone for the growing internet in the U.S.
Okay, so we have ARPANET for defense and research, then NSFNet expanding access for academia. How do we get from that to the commercial internet you and I use every day? That seems like a big leap.
It was a deliberate and quite strategic transition, actually, managed largely by the NSF. NSF provided the initial seed funding to get universities and regional networks connected to the NSFNet backbone. But their policy explicitly stated that this funding was temporary. The expectation was that once a critical mass of users and traffic was reached, commercial providers would step in to offer internet services and the network would become self-sustaining. They actively encouraged commercial use and interconnection. By 1993, this strategy had worked. Commercial internet service providers, ISPs, were flourishing, the NSFNet backbone was retired, and the transition to a predominantly commercial internet was complete. It's a fascinating example of government investment building the core infrastructure and then strategically withdrawing to allow private industry to take over and scale it up. And it's wild to think that the fundamental design, decentralized, packet-switched, built for resilience, using TCP/IP principles directly shaped by that early defense and research work, are still what makes your connection work right now.
Absolutely mind-blowing, tracing it all back. So the network infrastructure is developing, but what about making computers easier for ordinary people to actually use? We talked about command lines earlier. The graphical interface windows, icons, menus, that feels like another huge leap.
A massive leap in usability. And again, the roots go back to that federally funded research aimed at augmenting human capabilities.
Yeah.
We have to talk about Douglas Engelbart at SRI in the 1960s. His work, funded by DARPA and NASA, was all about improving how humans interact with computers. His legendary 1968 demonstration, The Mother of All Demos, was just jaw-dropping for its time. He showed off his NLS, the online system. It featured the first public demonstration of the computer mouse, hypertext linking, interactive text editing, collaborative tools, windowing displays, concepts that were utterly revolutionary. It was a complete paradigm shift from typing cryptic commands on a teletype machine. Engelbart showed a future where you could directly manipulate information visually.
So the mouse, Windows, hypertext, these incredibly familiar interface elements were demonstrated way back in 1968. That's much earlier than most people probably think.
Much earlier. Engelbart laid the conceptual foundation. Then Xerox's Palo Alto Research Center, PR, really ran with these ideas in the 1970s. PARC researchers, many inspired by Engelbart, developed the Alto personal computer in 1973. It wasn't a commercial product, more of a research prototype, but it was visionary. The Alto had a high-resolution bitmap display, meaning each pixel could be controlled individually, a graphical user interface using windows and icons, a mouse for pointing, and it was all connected using Ethernet, another PARC invention for local area networking. It was basically the blueprint for modern personal computing.
But if Xerox PARC had this blueprint in the early 70s, why did it take so long, almost 20 years, you said, for GIs to become mainstream with Apple and Microsoft?
That's the million-dollar question, isn't it? Xerox, despite inventing much of this, largely failed to commercialize it effectively. There are many theories why internal bureaucracy focus on their copier business, not seeing the potential. It took entrepreneurs like Steve Jobs, who famously visited PARC and saw the potential of the GUI in the mouse, to recognize the commercial possibilities and bring them to a mass market, first with the Lisa, and then much more successfully with the Macintosh in 1984. Microsoft followed with Windows, initially as an overlay on DOS, and eventually dominated the market. It highlights that recurring theme. Fundamental invention often happens in research labs, sometimes government-funded, sometimes corporate, like Park. But turning that invention into a successful, widespread commercial product requires a different skill set, market timing, and often a different organization. There's often a significant lag.
A fascinating, sometimes frustrating gap between invention and adoption. Okay, so interfaces are getting easier. What about the raw speed of computers? Was there a similar story with processor architecture?
Yes, definitely. This brings us to RISC reduced instruction set computing. The prevailing approach in the 70s was CISC complex instruction set computing. The idea was to make the hardware capable of executing very complex, high-level instructions directly, hoping to make programming easier. But this led to increasingly complex, slower, and power-hungry processors. Researchers, notably John Pak at IBM working on their 801 mini computer project, started exploring the opposite idea. What if you made the instruction set much simpler, much smaller, reduced? The theory was that these simpler instructions could be executed extremely quickly by the hardware, maybe one instruction per clock cycle. Complex operations would be handled by combining these simple instructions in software by the compiler.
So simpler hardware, faster execution, relying more on smart software. Did IBM run with this?
IBM did the pioneering research, but they were hesitant to commercialize RISC aggressively. Why? They were worried it would undercut the sales of their existing, highly profitable mainframe computers, which use complex architectures. The classic innovator's dilemma. Disrupting your own cash cow is hard.
So fearing cannibalization. And did federal funding step in again here?
It did, significantly. DARPA, as part of its VLSI, Very Large-Scale Integration Program, aimed at pushing microchip design forward, saw the potential of RISC. They funded two key university projects in the early 1980s. One at UC Berkeley, led by David Patterson, developed the RISC Pre and RISC-2 processors. The other, led by John Hennessy at Stanford, developed the METS architecture. Both projects demonstrated that the RISC approach could lead to significantly faster, smaller, and more power-efficient processors compared to the complex designs of the time.
And this time, did industry pick it up more quickly?
Much more quickly. There was rapid adoption by industry, spurred by these successful university prototypes and the availability of the designs. New companies were founded, like Sun Microsystems, whose Spark architecture was derived directly from Berkeley's RISC-2. MIPS Computer Systems was founded based on the Stanford work. Established players like Hewlett-Packard also embraced RISC. Even IBM eventually developed its own PowerPC RISC architecture. By the mid-1990s, RISC processors dominated the workstation market, high-performance computers used for engineering and graphics, creating a $15 billion industry. Technically, RISC was a boon for things like interactive graphics and virtual reality, which needed incredible processing power. Companies like Silicon Graphics or SGI were major early adopters of MIPS RISC processors. SGI, co-founded by James Clark, who had worked on the geometry engine for graphics processing with DARPA funding, built powerful graphics workstations based on RISC that revolutionized scientific visualization and special effects in movies.
Okay, so a clear link there between the need for graphics power and the adoption of RISC. Let's switch gears slightly to something that feels very current, but also has these deep historical roots: artificial intelligence. Where did the initial push for AI come from?
AI is another perfect example of long-term, patient federal investment being absolutely essential. The very early funding, back in the 50s and 60s, came primarily from federal sources, especially DARPA again. They were exploring Linklater's ideas of man-computer symbiosis and funding AI pioneers like John McCarthy at Stanford, who developed LASP, and Marvin Minsky at MIT. Big companies back then, like IBM or AT&T's Bell Labs, had some small AI research groups, but they often scaled them back. Why? The commercial applications were just too unclear, too far off. It seemed too speculative, too blue sky for their business focus.
So the government essentially acted as the primary incubator for the entire field in its infancy, taking risks private industry wasn't willing to.
Absolutely. They provided the sustained funding needed for foundational, exploratory research. Let's take speech recognition as a specific example. It perfectly illustrates the long time periods between initial research and development of successful products. Early work started with basic research by statisticians and electrical engineers trying to figure out how to analyze sound waves and identify phonetic components. Very fundamental stuff. Through the 70s and 80s, DARPA contracts were critical. They funded programs aimed at achieving large vocabulary, speaker-independent continuous speech recognition. That's the Holy Grail. Getting a computer to understand anyone speaking naturally without pauses between words across a wide range of words. This required huge breakthroughs in areas like statistical modeling, like hidden Markov models, computational linguistics, and just raw processing power.
And when did this decades-long investment finally start paying off in terms of actual products people could use?
It was a slow burn. Companies like Dragon Systems, which had received DARPA funding, introduced some of the first practical speech recognition for PCs in the mid-1980s. It was limited, maybe controlling the computer with simple commands, often requiring discrete speech, pausing between words. But thanks to continued research and Moore's law boosting processor power, by the 1990s, companies like Dragon and also Lucent Technologies were releasing much more robust continuous speech recognition packages. These were the direct ancestors of the voice assistants you have on your phone or smart speaker today. It took decades.
Decades of persistent effort. What about other areas of AI, like expert systems? Weren't they seen as an early commercial success?
They were. Expert systems were a different approach, based on capturing human expertise as a set of rules. If-then rules, essentially. Early federally funded systems like Dendril at Stanford could analyze chemical data surprisingly well. In the late 70s and early 80s, expert systems were heavily promoted as the first real commercial products of AI research. Companies sprang up to build expert systems for specific tasks like medical diagnosis or financial analysis. They had some success, but also limitations. They tended to be brittle, they worked well within their narrow domain, but failed badly if faced with unexpected situations outside their programmed rules. This led to a shift toward more flexible, knowledge-based systems.
And underlying all these specific AI applications were fundamental computing concepts also evolving with this federal support.
Oh, definitely. Take the theory of state machines. This is a fundamental concept describing systems that transition between different states based on inputs. Think of a vending machine going from idle to awaiting selection to dispensing. State machines are absolutely ubiquitous in modern computing. They're used in compilers to parse code, in operating systems to manage processes, in network protocols to handle connections, everywhere. The theoretical development and practical application of state machines grew significantly during this period, driven by the needs of AI, but also compiler design and communications, all heavily supported by federal research funding. You can even track the commercialization through patent trends. Between 1985 and 1996, AI-related patents grew exponentially, showing that the technology was moving beyond research labs and being embedded into real-world products, cars, manufacturing systems, software tools.
A long, winding path from abstract theory to embedded tech. Okay, one more area with fascinating military roots, virtual reality and computer graphics. You mentioned Sage had early interactive displays.
Exactly. The lineage goes right back there. Whirlwind had the first basic CRT graphical displays in the late 40s. Sage in the 50s had those interactive consoles with light guns. Operators could literally point at targets on the screen to select them. That's primitive HCI, but foundational. Then you have Ivan Sutherland in the 1960s. His vision of the ultimate display, a room where the computer could control the existence of matter, creating fully immersive virtual worlds, was incredibly far-sighted. His PhD work, Sketchpad, 1963, let users draw directly on a screen with a light pen, manipulating objects graphically. It's often considered the birth of interactive computer graphics. And later, his head-mounted display project, around 1968, funded by multiple agencies, including CIA, ARPA, ONR, and the Air Force, was arguably the first VRR system. It superimposed simple wireframe graphics onto the user's view of the real world.
Funded by the CIA and the Air Force, for what seems like the precursor to gaming headsets. That's wild.
Well, think about potential applications like flight simulation, data visualization, remote operations. The military and intelligence community saw strategic value early on. Sutherland's influence was immense. He helped establish major academic centers for graphics research at MIT, Harvard, and especially the University of Utah, which became a powerhouse in the late 60s and 70s, attracting top talent who went on to found companies like Pixar and Adobe. And VR research quickly found non-military applications too. Project Droopy at UNC Chapel Hill, starting way back in 1967, used VR and haptic force feedback to help chemists feel the forces between molecules as they tried to dock them together. This was funded by NIH, DARPA, and NSF, showing cross-agency interest in the potential.
Feeling molecules. That's an incredible application. How did this high-end research eventually trickle down to fuel commercial markets like entertainment and gaming?
It was really the relentless improvement in graphics hardware. It's driven partly by that RISC revolution we talked about. Companies like SGI, using powerful RASC processors and specialized graphics chips, like the geometry engine developed with DARPA support, made high-performance graphics workstations much more capable and affordable, though still expensive initially. This enabled breakthroughs in scientific visualization, industrial design, and crucially, film special effects and video games. The entertainment industry, especially gaming, became a massive driver for graphics innovation, constantly demanding more realism, faster frame rates, more complex scenes. This created a huge commercial market that pushed chip makers like NVIDIA and AMD to develop ever more powerful graphics processing units, GPUs. Interestingly, there's still a synergy. Military R&D continues to invest in areas like immersive training environments, large-scale networked simulations using standards like HLA, and realistic computer-generated characters. Commercial entertainment pushes the boundaries of rendering and interactivity. They often feed off each other's advances.
So it's a continuous loop, often starting with a military or research need, leading to commercialization, which then drives further innovation that might loop back. Fascinating. Looking back across this whole history, what are the big overarching themes about the role federal funding played? It seems absolutely foundational.
It truly is, and there's a solid economic rationale for it, often framed as addressing market failure. Private industry is naturally focused on shorter-term R&D with clearer commercial payoffs. It's much harder for a single company to justify investing heavily in very long-range, fundamental research where the applications are uncertain or distant, or where the resulting knowledge is hard to keep proprietary. Knowledge often acts as a public good. Once discovered, it's hard to stop others from benefiting, costly exclusion. And one person using it doesn't prevent others from using it, non-rival usage. This means private firms might underinvest in creating fundamental knowledge because they can't capture all the benefits. That's where government steps in, funding that basic high-risk research whose benefits spread widely across society.
So it's not just picking winners. It's about investing in the foundational science and engineering that enables future winners across the board.
Exactly. And the investment has been substantial and consistent across multiple agencies: DoD, NSF, DARPA, NASA, Department of Energy, often matching or exceeding private R&D in critical early phases of computer science and electrical engineering. And it wasn't just funding projects. Federal support was crucial for building human capital funding, university research, graduate student fellowships, which dramatically expanded the number of PhDs and highly skilled engineers in these fields. It also funded essential infrastructure, shared university computer facilities, high-performance computing centers like the NSF supercomputer sites that brought academic and industry researchers together, fostering collaboration and speeding up innovation.
It really paints a picture of a complex ecosystem, not just a simple pipeline from lab to market.
Precisely. This history completely blows up the simplistic linear model of innovation, basic research applied, research development product. Instead, it's this dynamic, messy interplay. New companies spin out of universities, sometimes fail, but their ideas and people move on. Federally funded research leads directly to products, sometimes bypassing traditional corporate R&D. Think about it. Relational databases pioneered at IBM, but really commercialized based on NSF-funded work at Berkeley. RSC prototyped at IBM, pushed into the mainstream by DARPA-funded university projects, the Internet ARPANET to NSFNet to commercial ISPs. It's rarely a straight line.
Right. It's much more like that winding river metaphor we touched on: tributaries, unexpected currents, feedback loops. What does this inherent messiness or nonlinearity tell us about how we should approach funding and managing innovation today?
It tells us that flexibility and a long-term perspective are absolutely critical. You need to be willing to invest in foundational capabilities without demanding an immediate, predictable product. You need to accept that initial goals might change radically. ARPANET wasn't built to deliver email or the World Wide Web, but those became its most transformative applications. Value emerges in unexpected ways. So, funding structures need to allow for exploration, for pursuing promising leads even if they diverge from the original plan. It requires trusting researchers and fostering collaboration across sectors.
And you mentioned the movement of people. That human element seems crucial for bridging the gaps between research and application.
Absolutely key. Technology transfer happens most effectively when people move researchers taking their knowledge from a university lab to a startup, or from a government project into private industry. We saw that with the speech recognition experts moving between IBM, Verbex, and Dragon systems. Collaborations are also vital. When IBM participated in the SAGE project, they gained firsthand experience with core memory, which allowed them to commercialize it rapidly. That close contact between research and application is invaluable. And finally, you need savvy program managers within the funding agencies, people like those historically at DARPA and NSF, who have the technical expertise and the flexibility to recognize breakthroughs, pivot programs when needed, and balance the need for accountability with the inherent uncertainties of research. They play a crucial, often unsung role.
So bringing it all together, this ecosystem of federal funding, university research, industry involvement, and talent mobility, it didn't just create technologies. It arguably built the foundation for U.S. leadership in a whole new global economy.
Without a doubt. This entire innovation system, nurtured over decades by strategic federal investment, is a major reason why U.S. firms like IBM, Intel, Microsoft, and many others came to dominate global markets in computing hardware, software, and services for so long. It spurred the growth of massive related industries, data processing, IT services, software development, creating millions of high-value jobs and fundamentally reshaping the economy. It powerfully demonstrates how long-term government investment in fundamental science and engineering, often initially justified by defense or other national needs, can have truly profound, cascading economic impacts that benefit everyone.
What an incredible, complex, and often counterintuitive story. We've traced this arc from literally aiming naval guns more accurately through projects like Whirlwind and SAGE driving real-time computing and memory,
To the formalization of computer science, the birth of crucial languages like COBOL and ALISPI, and DARPA's vision leading to interactive computing, time sharing, and the ARPANET, the seed of the internet.
right through to the graphical interfaces, the mouse, RISC processors, the decades-long development of AI and speech recognition, and the visually stunning worlds of computer graphics and VR. Every layer of the digital world you interact with has fingerprints from this history.
And the recurring theme is that symbiotic, often nonlinear relationship between government funding, laying the groundwork, academic research pushing the boundaries, and industry eventually scaling and commercializing the breakthroughs. The impact of those early, often military-driven investments has been truly profound and often completely unexpected.
It really makes you think. If past innovation was so often driven by shifting strategic needs, military threats, economic competition, scientific curiosity, what are the driving forces today? What unforeseen challenges or maybe quiet research areas might be shaping the next wave of foundational digital technologies right now, perhaps in ways we can barely even perceive?
Exactly. Think about fields like quantum computing, advanced materials science, synthetic biology, neurotechnology, maybe even fundamental physics research. It's often hard to predict where the next Whirlwind or ARPANET equivalent might emerge from.
A great question to ponder. How might today's niche, specialized technical research, perhaps seeming obscure, now become tomorrow's ubiquitous world-changing civilian technology? History suggests it's not just possible, but likely.